So, welcome to Adventures Yufeng. It's just me today. We'll be exploring custom containers with ML. So, yeah, let's get started. There's, not much of a intro this time. And let's move over to our coding screen. All right, so today what I wanted to try out was custom containers with GCP AI platform. Let's see what we get. Hey, look, it's me down here. We'll just go through here. So I want to show the workflow, right, of somebody coming to this for the first time and what that experience would be like and what we encounter and how we overcome those kind of hurdles and things like that. So we can see here that there's this process. We have this getting started, very nice, all about custom containers. And it's really this kind of custom version of AI platform training, which is kind of has a number of built-in pieces. So if I pull up my console, we'll be able to see kind of what AI platform training supports, which is like there's a handful of preset environments, notably around TensorFlow, scikit-learn, Keras, and the such. But then you need, you can do more custom things. So let's go to AI platform, and I'm going to bring this over, make sure it's in view here. Let's see. Oh yes, and as always, the live chat is open. So if you're on, please hit up the live chat over here or down below the video, depending on how your browser is set up. I'm type something there now. This is live. Type something. All right, great. And over here we have our training jobs, right? So you can start training jobs manually. I have a lot of random stuff, much of which failed because tweaking things. And what's interesting here is that you can really do any container you want, right? And so we'll skip past the setup for GCP projects and figure out this, the Docker installation process. And so to give us a clean slate, I've chosen not to install Docker in advance. Now we'll see if that comes back to bite me real bad, depending on how long it takes and how well or not well that goes. So we can see here, we want to add my username to the Docker group. So you can use Docker without using, so that's nice. So, but first they want us to install Docker. Very important note. So we see prerequisites, operating system requirements. This is the Linux version of Docker. Yes. Do I have to install Docker to use this? Maybe I can get away with this without using on the local command line. So what we can do is, let's jump over to AI Platform Notebooks and we'll run Docker from there. Well, assuming that Docker is installed, and just to give us a kind of side path, I'm pretty sure Cloud Shell has Docker installed. So worst comes to worst, we can always do it there. So we got two options. Since I think I'm going to pass on running it locally, if for no other reason than the fact that I'm streaming this out and adding a Docker build to my local environment doesn't seem like the smartest thing to do in the world. Cool. So we have Docker here, I believe. Yep. And I'm going to make this bigger. And we'll see kind of this workflow of local versus in the shell. So Cloud Shell is in the cloud, but you want to use it kind of like a local terminal. It's not really local, of course, but it doesn't sit inside of any of your virtual machines the way SSH into your virtual machines does. I'm going to tweak a sound setting here real quick. Okay, so hopefully, yep, you can still all hear me. And we want to install Docker. I want to check to make sure this is still good. This guy's still booting up, so let's go over to this thing. Okay, seems to not complain about that. We have Docker, we have this set up, open Docker. I really hope this doesn't assume that I'm not on, oh, okay, use gcloud as a credential helper. So maybe these are already run. So let's see what happens when I run these. Will it, okay, so it's doing a thing. Open Docker, ensure it's running. Oh, it just returns the time and date, okay. And it does that pretty successfully. No Linux, copy paste, always getting me. All right. So that's good. I'm gonna make this bigger here. And let's see, it gave me a warning. It contains these credential helper entries. And then we want to have a storage bucket. It looks like it wants me to use something. So we'll open cloud storage in a separate bucket because I'm sure we're going to need to be flipping back and forth between these a bunch. And great if I could find it. Okay. And then we have bucket name. You can use whatever name you want. This is where I like to have a text editor because I'm going to forget what any of these are, and later if I want to rerun these sorts of things, I want to be able to have this kind of runnable as a set of script commands. Let's put this in a new bucket. Let's call it, let's see if we can get away with calling it custom containers. I'm going to guess that's taken, but you know, can never be too sure. Oh, nobody has custom containers as a bucket name. That's pretty awesome. And we want this, oh, and my Jupyter Lab is open too, so we can try it with that. That'll be a more powerful machine, so that might be nice. Does it say what kind of bucket I should make it? Same region where I plan on running jobs. Yeah, so not multi-region. That's important. So you don't want to have it on the default. I'm over on the East Coast, so I'm going to do US East 4, and we can just choose standard. That's probably fine. And I'm going to leave the controls on their default. So we'll let that create. And can't believe I got that bucket name, but not going to complain. All right, let's continue running this in Cloud Shell for now. We'll see if we run into any compute constraints here. And then select a region for your bucket and set a region environment variable. That was US East 4, so we'll set that. US East 4. It's interesting that they put quotes on this one, but not quotes on this one. I don't think you need quotes on either. I'm going to venture to guess. But you do need no spaces. So if I do echo region, echo bucket name, hopefully these are all there. Great. Clear up this space problem. And perhaps that's where the quotes could have helped me out. Of course, there was no quotes on that one. Create the new bucket. We did that. Download the code for this tutorial. Great. I'm going to, let's see, this is just all the CloudML samples. So we can drop them into here for now. That's fine by me. I'd like to actually pull them into my local at some point so I can play around with them and look at it, you know, with a better browser. But for now, this will do. Also nice because this doesn't hit my internet at all. This download and unzipping all just happens in the cloud in that Cloud Shell directory. So if we go to this path, we can load up the PiTorch sample. So this is CloudML samples. And again, apologies for the terrible font sizing. I made this bigger, but it doesn't seem like it. It kind of makes the font here bigger, but it's not a whole lot. I'll keep this in view here. And what is it? PiTorch containers. And MNIST. So there's a couple of different quick starts. MNIST is fine, I guess. We can replace it with something else should we be so inclined. All right, what else we got? I wish this could go away now that I'm like really browsing into it. If it could like fade away or something. Create a custom container. So we'll need to make our Docker file. So if there's anything I've known from the Docker world is it's all about Docker files. So we're going to make a Docker file. I can't believe this guide is still on Python 2.7. It'll be really interesting to see if I can push it up to Python. I'm curious. Push it to like 3.6, 3.7 and just like see if it just randomly works. That'd be pretty good. Let's open that in another tab. And yeah, why not? Let's, you know, we're experimenting with stuff. Let's see if I can't get it to go with Python 3. I don't know the exact you know, full name for Python 3. So Docker file Python base image, not base 64. Supported tags and respective Dockerfile links. All right, seems good, pretty promising. Yeah, there are a lot of different options here. Why you shouldn't use Alpine. Longer build times, small images, and obscure bugs. Okay. Option 1 is Ubuntu LTS and CentOS and Debian. All seem pretty reasonable. I'm pretty sure. Thanks, Ron. Yeah, this is very much an adventure today. It's just me trying to figure stuff out. This is the real live coding experience, as it were. Yeah, let's see if I can find Ubuntu or Debian, because I know the GCP images are default to Debian images. So where was I? I lost my place. It's always good. So this is Python Jessie. So here's our list. And it suggested Buster, right? That was released in July 2019. So we have these Buster ones. And so if we do something like, I don't know, I want to make sure I have, what is it? F strings are the best things ever. So I want to say that's only in Python 3.7, or is it in 3.6? When did it come out? If anyone remembers, they joined part in 3.6. Okay, so I want at least 3.6. So here we got 3.6, and if we have a good 3.7, I'll take that as well. But like something like this would probably do the trick. So this is, all right, so we'll just fingers crossed, make it work. And we can always fall back if this thing completely blows up in my face, but let's see, it seems to be pulling the create the correct URI and build the Docker image. So it runs Docker build, Dockerfile. Oh, okay, it pulls the local Dockerfile. So where are we here? There's a Dockerfile here. Okay, I can just edit it directly in place, which is nice. It looks like, yeah, this is the one we want. So I'm gonna replace this with that. That should do the trick. Save that, and then we'll just run this. And fingers crossed here. So that set a bunch of parameters. I'm going to hit enter. I'm going to make a note here. This is kind of part of my own workflow. I want to make sure I record what I'm doing because this way when I come back to this some other time in the future, I have it. So we have the repo name, we have the location. I should probably make a note from earlier what we did where we grabbed this and then CD'd it down. So I'm going to take these commands down too. And while it's true that I could probably just get this with a history command after I finish today, a lot of times you have some intermediate steps that you kind of chose to go back on, redo, because I suspect something here is not going to work, unfortunately. So I'd like to still break it up. And I am in some ways reproducing the docs manually and in a stripped down form, but I've found it to be a pretty clean way to just get the bare bones, right? So get the files for sample and CD. So this is setup. This is container name, and then we have our Docker build. Cool. And where were we? How's our build looking? All right, so it looks like it did not like it on the download of Torch 1. It's it's funny, it's on CPU 3.7, so it's looking for the correct version of PiTorch by all indications at least. And where is this tripping up? Newer image, grabbing the stuff, and then it says run pip install torch 1.0.0. My first thought is whether or not this is the right, if torch 1.0.0 is the most recent version. So I'm going to go over to the PiTorch documentation, and I had 3.7. Does PiTorch not work on 3.7? That's always possible too. So luckily, these are the kinds of things where if I were running this on a local machine, I'd have to go redo Python from scratch, right? Which is no fun. It looks like PiTorch 1.4 is available now, so we're quite a bit behind. So if we say I want the stable build, I'm on Linux, and I'm doing it on pip, I'm on Python, this is what it suggests, just without any versioning. There's no indication of any kind of Python version support. Okay, supported distributions, Debian support is there, we're at 10.0, Python 3.6 or greater. Okay, so we are there, we have 3.7, and everything else looks right. It might just be that PiTorch 1.0.0 didn't support 3.7. I mean, 3.7 is fairly new compared to when 1.0 came out, so that's understandable. Yeah, let's just update this to 1.4. I'm going to take that part away, and I don't know what version Torch Vision is on, so I'll leave that blank as well. So let's try running this command again, and see if we can successfully build this image. I gotta say though, this overall is a lot faster than, say, trying to kind of set up your own environment from scratch. So promising, all things considered, from like working with containers as a workflow standpoint. Pretty interesting. So this is doing its thing. It's still CP37, so that's interesting. We'll have to see if this leads to any issues down the road. And oh, that blinked offline, so that's not great. So it's still complaining. At this point, I might drop back to using the, just testing it to make sure the command as given works. I think what's interesting here is if I take away some of this noise, if I do Docker, let's see what that gives. Okay, out of memory error. Okay, so there we go. Now we know it's the issue is not with the way this was set up, but more that Cloud Shell itself isn't big enough to handle the size of this image. Now we can click Boost Cloud Shell, and it'll get us some extra stuff. It will restart our VM. So instead of doing that, since that'll start everything over again anyway, let's start from scratch again, but this time in this VM that I've created. It's a more full compute cluster. I mean, it's still nothing crazy, 4 cores and 15 or 16 gigs of RAM or so, but at least it's not nothing. So I've got a terminal here. What directory I'm in? Am I in? So I'm in home/Jupyter. Let's do let's see. Let's go here and make this bigger. And I've got an empty directory to start with. Great. And we're gonna now get to reuse some of these commands that we had to do earlier. So I'm not entirely crazy for copy pasting some of that out. We're gonna re-download these files to this new location. Should I put it here? Yeah, this is fine location wise. Yeah, I cannot. Denied. Wow. Is it because I'm signed in as the I'm guessing it's because I'm signed in through this notebook authenticated with the service account, and so I can't write to this folder. which is surprising to some degree. So it's still blank. I can't even download to it. All of the protections. Okay, that's fine. We'll just go back to the Jupyter folder where I have a bunch of noise. It's fine. Paste that all in. It'll download. It'll be fast. It will unzip, and we'll CD into this path. Great. Okay, so yeah, the Jupyter username is home here. So that's where I have write access. And then we need to edit these Docker files like we did before. Let me close down some of these other tabs that I had from last time I was using this VM and go into our folder. So we have it open, PiTorch, containers, quick start, mnist, Dockerfile. And there it is. So I'm going to pull this aside and copy the new Python values that we had. And we also updated this line. Come on. Great. Save that. Always remember to save. And we're going to run this again. So hopefully this workflow works. It might mean we'll run into other issues down the road if we're not careful here, because I've installed a different version of Python, a different version of Torch compared to what the guide says, but they are more recent versions. Hopefully that means they'll be still compatible and still kind of backwards compatible, so to speak. So this Dockerfile, it says it also installs a number of other dependencies, including hyperparameter tuning libraries, the Cloud SDK, which is great. And at the bottom, it copies the code into the container itself. So it takes the code from this directory, it looks like. It takes, I'll use the actual copy that we have here. It's a little bit bigger. This copy operation copies the folder trainer from this local location to inside the container root/trainer mnist.py. So there's that mnist.py file, and it's telling it to start there. But what's interesting is it's calling Python directly here. Hopefully it doesn't have to be something like Python 3 like that. Hopefully by setting the Python version as 3, there's no kind of Python 2 in the background lurking. I've had problems with that before on like actual VMs. I haven't seen this happen in containers yet, but I have limited containers experience. Okay, so this is still going. And let's look ahead while this is running. We had this Dockerfile, we ran this command, and we're going to verify it by running it locally, and we're going to pass a small number of epochs. Yeah, that seems reasonable. So once this is done, I'm going to test locally with only one epoch. That's a good note to take. I want to make sure there's a space there. Great. So this is what we're going to run next. It's still installing libraries. All the dependencies. What can you do? And then once we're happy with this, so what's interesting here is that it's running the container we've built, which theoretically you would be wanting to build something that if you're shipping it off as a container rather than just running this training locally, you'd probably be trying to do a big training job of some kind, right? And so it raises the question sometimes of like, why would I care then to make this container? I could just train it locally. I'm rerunning the container here locally. And so that's where structuring your code such that you're able to give it, maybe not in this case, it's just you can short circuit it and say I just want one epoch, but you could also imagine having an argument that allows you to pass in the path to the files that you wanted to train, the directory of files you wanted to train on, and that perhaps you could point it to a smaller version or a smaller subset of your data versus like the full data set. And so that also gives you kind of this flexibility to really be able to use this tooling and make sure you test your code before you try kicking off a big training job. So we're all done here. It's great. And we're going to run this image this one time. It's showing a bunch of percentages for some reason. So that's something. So this is perhaps a good opportunity for us to take a glance at what exactly that we're running, right? Why is there a bunch of percentages being displayed and just hanging here now? I have no idea. let us see. It's using Torch, it's importing, it's got a model file name, and we're gonna create a convolutional network. It's the feed forward pass is a ReLU of max pool of the 2 convolution layers, pulling a view, another ReLU of self, fully connected. So that's 320. So what is this? A 1x10, a 10x20, and then 320, and then a 50. Seems fine. I wouldn't personally do a kernel size 5 for MNIST, which is only 28 by 28. You might want something a little bit bigger. Depth of 10 and 20, that'll be fine, it'll work. Training, it says it prints train epoch. So we're expecting it to say train epoch something, right? Why is it saying this percentage thing? That's kind of concerning. That seems to be one of only a few print statements. I suspect that in the real version, it's supposed to just print these 2 statements and be done with it. It's relatively straightforward. We see there's a bunch of arguments here that it can parse, which is generally speaking good practice. A lot of data loading. Oh, maybe those percentages are downloads when it's downloading the data files. That's something potential. Log interval. So batches to wait before logging. Training. Let's peek back over here. Still nothing. Might have to kill that process. We can set seeds, we can add momentum, we can set learning rates. Lots of good arguments here. Batch size as well as test batch size for when you run the evaluation or your testing. Okay, I'm torn on where to cut this because I know MNIST can take a while to train sometimes if it's like a big thing. And I didn't use the Docker GPU version, and I technically have a P100 attached to this VM, so maybe I should have done that instead. Something to ponder over, I suppose. What's this file look like anyhow? Is it considerably more involved? So it's pulling from NVIDIA CUDA 9, which I feel like could stand to be updated. Where is the Python install though? Because I'm guessing maybe NVIDIA's CUDA install already comes with Python, but then we would need to specify Python 3 versus 2. Here we are. Installs pip. Oh, that's just an install pip. I suspect that might be Python 2, so that would be interesting if we tried that. We are already almost halfway through. This thing is tripping on itself. Let's cut it and see what kind of where it was stuck on. Downloading. Really? It was stuck on the download? Come on. You've got to be kidding me. Let me just see if this even... Aha. So, it looks like the classic MNIST, well, wouldn't count it out yet. Maybe it's... Oh, no, it's still there. It just can't connect to it. Now that begs the question. Why can't our container hit the internet? Maybe ping doesn't work that way because I know nothing about networking. So downloading, extracting, downloading, extracting, downloading, no extracting. So it did get stuck on the last one, the labels data set. Let's just try running it again because, you know, the usual IT troubleshooting is stop it, start it again, kick it in between, shake it, wait 30 seconds, unplug it. Have you tried plugging in your monitor? All right. This is dicey because it's still stuck on a random percentage that makes no sense, whatever 180.4% means. So let me do this. For today, we'll go with them. We'll go with their original plan and pull from Python 2. I just don't see how Python 2 has anything to do with this. I think we're going to Oh, and there it goes. Okay, so it finished. That's a relief, firstly. Secondly, this is, for one epoch, it gets to quite good accuracy, which is hilarious, but that's what you're going to get with convolutional neural nets, you know. High accuracies, not necessarily high usefulness, depending on, you know, if you're not careful on things. All right, that's enough of that. Let's go down to, yeah, that table of contents with the quick links at the top should be here, not this whole thing. But I bet if I widened this, it would work. But then you guys all can't see it. So let's see, we want to push it to the image repository. Let's do it. I'll start it before I take notes again for the sake of time here. All right. Push to image repo, also known as GCR, Google Container Registry. So it's important to, you got to push it up there in order to, or some registry in order to make your containers run, for better or worse. You can't just say like, oh, just grab it from my local machine over here in this place. So it's pushing each one over. As you can see, it's a not trivial amount of, I don't know, network traffic, but all within the Google network. So A, I think it's free, and B, none of that is coming from my home machine because this is a VM in the cloud, which is great. And it means I can still, you know, browse my documentation without this like bogging down my machine. So we're going to set some model directories and regions. So the region should be the same. All right, let's see. Submit job. So what we're going to use, if I'm not mistaken, is this will run on AI platform training. We got the date. We got PiTorch model. Let's do PiTorch MNIST. And let's do torch MNIST date and right, the value of date, blah blah blah. We have the region already, so I'm gonna take that away. Not least because it's not US Central 1 anyway. So, but we already exported it up here. Oh, but it's an export call, so it might want that. Should be the same. Job name, custom container job. Ooh, that is a long name. Firstly, we know it's a job because it'll be a job, so I don't need to say job again. It's, you know, factory. And let's see how we're doing, see if we're ready to submit the job. Okay, so we are ready to submit the job. Let's set up these environment variables. Obviously, that doesn't do anything. This is the big command, right? This is the important one. We're gonna submit the job, and let's see what kind of arguments it's passing. It's passing in 10 epochs. I'm gonna say we're just gonna do 4 epochs for the sake of time. The most notable thing here is, right, we have this model directory, which we pass in here. We have our bucket name, which we set at the top of this, at the very beginning. And this image URI, which is what we just pushed up to Docker. And we have our region, of course, to tell it where to run this training job. And importantly, that's the same region where we've stored our data. So that means that everything will be basically in the same kind of geographic area, which helps keep everything performant. So let's kick off this training job. So I'm on a VM, right? I could run this training job locally on this machine. The point of this exercise, if you will, is that you're basically rerunning the same code, but with more data or for longer, or you're doing hyperparameter tuning, so you're running lots of models in parallel and then tweaking numbers. And so now that's off. Just as my local machine has been freed up this whole time with nothing more than effectively an SSH connection to this Jupyter server, so too now is this virtual machine freed up now that I've sent off this training job, and I can check, you know, play around with the code, try a different model, try a different data set without having to worry about the impact of running this training job locally, right? And having kind of a noisy neighbor effect here. What did I submit though is the real question, because there was no config. .yaml. So usually when I send a AI platform training job, I send a config file which specifies kind of the machines, how big they are, how many there are. So I want to see what exactly I just submitted, because if it's just a CPU thing, I'm going to have a bad time. And with this kind of AI platform training, firstly, it's important to point out that they call it jobs, right? We submit a job, and that it's not training right there. And then when we're done training and we want to serve or we want to have predictions, there's no predictions option here. It's called models. So in your mind, you have to map training is jobs, prediction is models. So just a little tip there. And when you do submit these jobs, there is some amount of preparation time as the machines get spun up, the libraries get installed, or in this case, the container with all those libraries kind of specified gets pulled in, right? They need to download that container, which is not insubstantial. We can see this training input. We have our config file, we have our image configuration, and we can see that it's pretty normal. There's no extra JSON. Oh, right, that's the training output, so there's nothing to see there. It's very interesting that there's no, and I don't know why there's a GPU tab, because there's no GPU involved in this particular job as far as I'm aware. And so that'll take a few moments here to get going. Our Cloud Shell instance is pretty much useless at this point, so I'm going to close that out. And wait, before I do, I wonder if there's a way to turn off the boost. Oh, I never started it, right? Yeah. So we'll get rid of that. And let's see, we have sent off this training job. Hopefully it works and we can do something with the resultant model, because we did set a model path. So let's show that. This model directory, it looks like it's just within that container. So it'll be very interesting to see where this ends up. Let's see if it talks about this out. Within your cloud storage bucket where your model file is saved. Okay, so this is a directory within the, this is model directory. Okay, so what we've actually passed in was this value. So if I echo this, assuming that this will parse correctly by echo. There we are. So this is the actual path where our model will end up. So it'll be in custom containers slash, paste it up here, slash adventures torch mnist 2020 04 03, etc. So that adds up. And let's see, it appears to think that it's running. I'm going to open this in a new tab. And as you can see now, we have the notebooks dashboard, so I don't forget to turn off my machine when I'm done. We have our training job. I have logs coming online for that training job. Got the actual Jupyter notebook, and I have a cloud storage tab. So that's 5 tabs just for cloud storage. You all can't see that, can you? Why has no one told me of this? All right, here we are. Here are the tabs that we're dealing with here, right? So we have all of these tabs and this Google search. Close out some of these notes on Python. I'll leave the PiTorch docs up for now. Seems like we've already written something to here. I don't know that this job is finished per se, right? But we've begun to write something to it. So we can see here, we have new features in the logger preview. Fancy. We can see here that's on the Epoch 2. And I'm going to scroll up here. We got all sorts of goodness. I'm going to open one of these, see what it actually looks like. Okay, so it shows our progress and our loss. Nice. And I think at the end of here we go, we have an average for that epoch. We're at 96% accuracy, and now we're on to Epoch 3. It's doing its thing. It's making its way through. So that's where we're at now. It's still going, flying through. We're on to Epoch 4. In between Epoch 3 and 4, we got to 97%, and we're on Epoch 4. And ooh, they got some warnings here. What's going on here? It's probably starting to write out a does it say what the file is? That's probably that file that we saw pop into here. Where did it go? Torch.model. Okay, so it's because it finished. And so we're doing the thing. All right, so at the end of it all, that's the end of it. Interesting that the write hit the logs before it finished getting all of these values. So 9,717 out of the 10,000 images in the test set where it got right. And now we have a torch.model. So now what we can do is we can take that model, we can deploy it. Let's see if this guide talks about that at all. Okay, it actually just jumps straight to hyperparameter tuning, which with 20 minutes remaining, we might have time for. Interesting. Right, so this Dockerfile we were using already includes the CloudML Hypertune package. And so all we need to do, let's see what we need. The job request requires a few more arguments. In this case, we tune learning rate and momentum to minimize the model loss. Fair. Now we get to create our config.yaml. Great. So it is doing it via using cat, which is horrible. I'm just going to do it this way because it's the sensible thing to do here. Assuming that I can manage to config that. I made it with a bracket, didn't I? Yep. It's good. It's real good. Config.yaml bracket. Where's rename? Good stuff. Let's open that up, paste this in, and save it. Right. And we have learning rate trying from 0.0001 up to 0.1, and we're going to try momentum values from 0.2 to 0.8. Trials up to 5 at the same time with early stopping enabled, which is nice. All right, so that looks solid. So we've saved that file, and let's see what this dealio is here. Hyperparam tuning. We are setting a new, okay, so this is worth pointing out. See, we're setting a new model directory. So we had it up here, and we have it down here. And so this time, it'll always be different because that datetime. So you can, just rerun the old command again because it has the date captured. So that's convenient. But because we're doing a hyperparameter tuning and we know it's a model, so I don't need to put that. That'll be good. We have the same region as before, so I'm going to change that there and get rid of central. And we know it's a custom container job. It's hypertuning. So the job name, model directory name are slightly different. I might be inclined to put the state in front so that it sorts better. Hopefully that I don't end up paying for that. Okay. Let me run this command in our Jupyter Notebook terminal thing. I mean, I could just SSH into this and just have a terminal, right? But then I don't get a convenient editor next to it. So Jupyter Lab for the win. Now let's go back to here. We have our command that we're going to run. Let me remind myself, make a config.yaml for hyperparameter tuning. Very important. I can't spell tuning. It's good. All right. What's changed here? We're going to change this epochs to 4 again because I wanted to. And here now we finally have a scale tier, right? So I'm not sure why they chose to go with scale tier basic. Once I kick this off, I'll talk a little bit about the various scale tier options, which refer to the compute that sits behind these training jobs. But essentially, it's a way to choose how big you want your machines to be. What did I do wrong? Job ID. So I've chosen job ID to be the job name, and this is what I get. This is what I get. For flipping, I did one thing, you know, and I break it. So let's see what I had for job name. So job names apparently can only start with letters. No, should start with a letter. I think what they really mean is must start with a letter. So I'm gonna fix that and just put a in front of it, because that'll fix it, right? And then we're going to do this. So later when I have a random A appear in front of my job ID like it does here and I'm confused, you can tell me why. And then let's see. Okay, let's talk about scale tiers while this training job goes off. So we should see that training job succeeded. If you caught that for just a moment, here it is. And you can see here we've made this training job. We have hyperparameter tuning set here with learning rate. Yes, learning rate. And we have a target metric, which is interesting in that when we set it up here, what did we say it was? It's just a tag. So I assume that here, look at that. So the code has a little hypertune code. So it uses that SDK that was installed to set a name for this tag. So good thing I didn't change it. And the actual value is this test loss value that is computed here. So it's basically tying and naming the metric that you want hyperparameter tuning to point at. And this is just a way, it looks like, to associate the variable name to a string value so that you can point at it and call it something, rather than just exposing a variable like pointer, basically. Okay, so let's look at scale tiers. And then we have GPUs with custom containers, which I don't think we'll have time to cover today, but it looks like it's start over again and do the same, but pick the Dockerfile GPU version, right, which installs all the NVIDIA drivers for us. It's nice that you know, you can get all this CUDA and cuDNN stuff pre-installed, though. That's definitely a nice way to go. So yeah, with the time remaining while this training job runs, let's go ahead and talk a little bit about scale tiers and how you can think about the options you have. So over here on the left, in this panel, we have all these things about different options, things to get started with. We have this training workflow, you know, we're monitoring training jobs, running training jobs, specifying machine types or scale tiers is the article that we're going to kind of dig into a little bit here. And specifically, this page talks about how to configure your training job in terms of the compute that you're looking for. And you can see that, you know, it can get rather verbose. You can say scale tier custom and then pass in all of these arguments manually, but you should probably prefer to pass them in as a config file. Now, if I can find an example of this. All right, what do we got? Train with GPUs, TPUs, memory. Okay, so I think it's at the top here when we saw something like this. And there's ways to do it. Apparently, when you, okay, this is still via the same API though. So we'll go with gcloud. And you can see here that this config.yaml for a custom processing cluster allows you to choose a master, worker, and parameter server. So you have this structure where you have a master node that is controlling your distributed cluster. You have parameter servers, they're doing the heavy lifting. And then you have, workers, they're doing the heavy lifting. And then parameter servers are purely to sync up all of the variables across the different workers. And so you can imagine this, you know, everything's at the top with the master and it's talking to the parameter servers, which are connected to all of the parameter servers, which are of course connected to all of the workers as well. So it's kind of like a web layer underneath and the master is coordinating everything. And you can choose the machine type for every single one of these machines, master, worker, and parameter server. And you can also specify how many you want. You want how many workers, how many parameter servers, and there's rough guidelines around kind of what the ratio should be, how big the machine should be, and a lot of it depends on the particulars of the model that you're training though. Now you'll notice that with this approach, having a config.yaml, you can pass in this configuration flag and pass in that file name, just like we did here. Now with us, the file that we passed in is kind of random, not random, but like it doesn't talk about the actual machines it wants to use. So that's why it also has a scaled tier specification here. Whereas in the docs in config.yaml, scale tier set is custom. So there are other values aside from custom, of course, and one of them is basic, and I'm pretty sure there was something else. A lot of this is kind of legacy information here. So these were the quote unquote original scale tiers, right? And you have choices like basic, standard, premium, basic GPU, basic TPU, and custom. And custom is just everything else. And so there's a couple of choices, and basic is an N1 standard 4, which is, I believe, the machine that I was using for here. Maybe. Does it not say? It doesn't say directly, but it's a 4-core machine, and it's standard as in standard memory that matches that. So I think that's what I have. A standard 1, which is a actual distributed setup. It's not a single machine, right? Basic is a single worker, but standard 1 is actually a distributed cluster, and it's just one pre-configured set, and you can see the types of machines using here. And so it's only useful if you're training with TensorFlow or custom containers, which in our case we are. And it has a master that's N1 high CPU 8, so it's an 8-core machine with high CPUs. The same machine for all the workers, and then parameter servers are N1 standard 4 again. And then there's premium 1, which the change here looks like you bump it up to 16 cores, and the parameter servers are high memory with 8 cores. And then there's GPUs that tie to a K80. It's unfortunate that there's no like premium or advanced GPU. There's only basic GPU. So most of the time, if you want GPUs, you probably want custom, because basic GPU is just N1 standard 8 with one K80, and these days you're not going to get a whole lot out of that. You should probably be using newer GPUs or more GPUs. And similarly here with basic TPU, this is good for just like basic TPU testing, perfectly suitable. But if you wanted to do more stuff, you should probably be doing a bit more custom configuration. And so custom then opens up a whole world of options. You have machine types across the wazoo, right? So I'm going to scroll down a little. You can do something as simple as this, where you just say the master type, and you just get a single worker. So that's how you would configure a single node custom setup. And there's lots of machine types to choose from. You have your standard, so that means the memory and the CPU are in a standard ratio. I think it's on the order of, I think it's technically 3.75 gigabytes per core. And so like a 4-core machine will have almost 16 gigabytes and so on. And then high memory, and then there's also high CPU. So it's all relative to that standard ratio. So high memory has more memory than usual. High CPU has essentially less CPU than usual. And so there's also legacy machine types, which kind of were the original values that you could put into these configs. I would recommend sticking with the standard ones today. You might see some of these used in demo code and samples on and off here and there. They use what they call t-shirt sizing and kind of complex versus standard models. And so you can see here there's standard models, large models, standard model S, complex model small, complex model medium, and complex model large. And so that talks about the notion of, they all map to real compute engine instances anyway, so it's not worth the extra kind of lookup table work to get this to work. And so there's a lot of options here. You can see there's more GPU options as well. There's medium GPU, large GPU. Unfortunately, they still all tie over to K80 GPUs. They're just bigger computers in the background. It's only when you have the standard and then it says P100. Now you're getting P100s. For instance, here, the complex model medium size P100, there's 4 P100s tied to that. So that's, not insubstantial. And then you have the V100s. And it's a similar kind of layout. So in that sense, you can get a little bit more options from here than in earlier, where GPUs, you basically just had this go custom. So that part might be handy. Though I want to say these are going to eventually go away because, why else would they be called legacy machine types? But yeah. And then we have training with GPUs and TPUs and some more machine types. So as I mentioned, N1 standard 4 is your kind of standard kind of thing. And you can see here the ratios, right? They kind of stay constant, 8 and 30, 16 and 60, 16 and 60, yeah. And then when we go to high memory, it goes 2 to 13, right? We have the same amount of memory, but only half as much CPUs effectively. And then when we go up to 4, it's 26, 8 is 52, and on and on. And then when we go to high CPU, right, high CPU 16, this would have normally given us, 60 gigs of RAM, right? 16, yeah, standard 16 is 60 gigs of RAM. But in the high CPU world, 16 CPUs is only 14 gigs of RAM. So this is literally less than 1 gig of RAM per CPU core. So really high CPU compared to the memory footprint. And then the further comparisons, these will line up with the descriptions above with regard to the kind of machines they have under the hood. All right, so hopefully we've talked long enough to have this finish. Apparently I was wrong. Let's see here. Let me make this bigger. Let's see, we've got a couple of trials that ran, so it's not nothing. We have different learning rate and momentum numbers. And we can see that this first pass took 7 minutes. So I'll let that keep going. Might have to cut the stream off unless people are clamoring for this to watch the thrilling finish of how good we can get our accuracy and loss down to. In our previous one, I'll dial back later and see what kind of loss we achieved, because with these lowish learning rates and lowish momentum values, this is relatively speaking higher loss, right? And then we have 0.055, 0.051, so it's definitely trending in the right direction. Learning rate got bumped up to 0.05. That seems to be a more reasonable number than 0.006, a little too slow. Momentum hasn't changed that much. And it could be a bit because it's trying so many iterations. Now, what we can do is we can go into the logs. Actually, I still have them open, I think. Right, we had this final thing. We had loss was 0.09 was the average loss from the first run that we did. And so given that the loss here, I think was 0.05 versus 0.09, that's quite good. We see the new set of trials have kicked off because we said only 5 trials at the same time. So 0.05 versus the 0.09, so almost half as few or half as many, half as much loss. So that's quite an improvement. I'd be very curious to see what test accuracy this comes out to or came out to. And I suspect that we can find it by trial ID maybe. So let's take a look at the logs for this one ID. Can we do that? Maybe? View logs, yeah. All right, so keeping in mind that we achieved accuracy of 97%, just because the training loss or the loss was lower, well, test loss was lower, so that should give us a good value. So that bumps up to 98%. So, woo, 9840 versus 9718 in terms of number of correct images in the test set, which was the holdout set and the training never saw. So that's quite good. I'm happy with that. Given that it was kind of just a random convolutional network, I didn't have to do that much work, and we did it in an hour, and just hypertuning gave us over 100 more, over 120 more accurate predictions. I think it would be worth visualizing that. I'd be very curious to see which 20 or which 120 they were, and how those improvements came about. But for now, we'll cut it here, and look forward to seeing you all next week. I'll be on again, 3 p.m. Eastern time. See you on Monday. Thanks.